Hey, so today we're going to be talking a little bit about energy and where we get the energy from and how we represent the energy. So after the spring lab, where basically what we did is we took and we stretched out a spring, and there's a couple different ways to do it. Here's one way. So you can take the spring and you can put it on a force sensor. So this is the rest length of the spring, and if you start pulling it with some force, it's obviously going to stretch. And so what we're looking to plot here is we're looking to plot, if I want to stretch it a certain distance, how much force does it take? I'm going to stretch it out. Stretch it out again. And I want to measure how much force the spring pulls back on. So this is the stretch distance, which we call x. And this is the force by the spring. So it's how much force is getting pulled back. And when we graph this, we get something nice and linear, which means if you stretched it out twice as far, the spring would pull back with twice as much force. No big deal. It's pretty standard. And so if we look at this in terms of y equals mx plus b, we see that on the y-axis is the force by the spring. And then we have the slope, we'll talk about that in a second. On the x-axis is an x, which is nice, and then the b value is 0. And so what goes here is something called the spring constant. So in this case, the slope is the spring constant. And it's a measurement of how tight a spring is. So a larger spring constant would be a tighter spring. We can see how this would manifest on this graph. If the green one were a different spring, we would see to get the same stretch distance, it would take less force. There would be a looser spring. Similarly, the blue one, steeper line, larger slope number, to stretch at the same distance, you would need much more force. And so to represent the spring constant, we use the small letter K, and we measure it in newtons per meter. So in the lab you guys got, for example, one of the springs was spring constant is 40 newtons per meter, which means that for every 1 meter of stretch, it's going to take 40 newtons. Now, not every one of these can be stretched a full meter, but if you were to stretch it a full meter, it would take 40 newtons. Or if you stretched it an additional meter, it would take an additional 40 newtons. So we use the letter K, so this is it here. So it's a small letter K that represents a spring constant. And this is something that we call called Hooke's law. It tells the relationship between the force, the spring constant, and the stretch distance. Now, if you look at it in the textbook, it's going to have a different feature to it, and I'll put it up here now. In the textbook, it has a negative sign, and the reason it has a negative sign is because the force and the stretch distance are actually both vectors. So this tells you not only how far you stretched it, but in what direction. And this Force is also a vector, and it tells you what direction the force is. So here's the deal. The reason there's a negative sign is because the stretched distance is in one direction, and the force by the spring is always in the opposite direction. So when I pulled it out this direction, this is my x vector, but the force by the spring is actually in the opposite direction. So this is the force that I apply on the spring. This is the force that the spring applies back on me. We know those two are Newton's third law force pairs, but you see that the force by the spring is in the opposite direction as the stretch distance. That's why you're going to see a negative sign there. But the question remains, where is the energy? So I'm going to take this and I'm going to redraw it down here. So this axis again is the force, oh no, this is the stretch distance. And this one here is the force by the spring measured in newtons. And so, if you take this graph, and in essence what we've done here is we've taken a spring and we've stretched it out at a distance x, and it's taken a force F to do so, we know that we have put some energy into the spring by stretching it out. So what we've done is we've done work on the spring. So what is work? When we talk about the concept of work, work is the transfer of energy by a force. And what that means is that I can apply a force to the spring and then store energy in the spring. We'll talk more about energy during the class period, but let's see if we can find it over here. Where do we represent the energy? Where do we represent the work? Well, the x-axis is the stretch distance, the y-axis is the force, the slope is the spring constant, so where's the energy? Well, it turns out the energy is the only place left on a graph, and it's the area. Drop this down. And so our definition here is that the work, W, is equal to the area is the area, and we say the area under, but it's really the area between your line and the axis. It's the area under the force distance graph. This is our definition of work. This is going to be a universal definition for work, and we're going to see how it manifests in a couple different contexts coming up. But let's see if we can't work this out. So if this is our work concept, if work is equal to the area, what do I notice? This shape is a triangle, so how am I going to get the area of this? Well, 1/2 base times height. One-half the base times the height. No problem, 1/2 xf. But here's a cool thing. The work done, if it's equal to x times f, we actually have an equation for f right here. I'm going to substitute this f into this f. Let's see what happens. So I have 1/2 x times kx. If I simplify that a little bit, the work done is equal to 1/2 k x squared. So this is the work done by stretching a spring if you stretch it a certain distance x. So 1/2 kx squared. Now what's nice about this is that the energy, the work you do is equal to the energy stored. So the work is equal to the energy stored. So this is the work done on the spring, and it's also equal to the energy stored in the spring. And we have a name for that kind of energy. The energy stored in a spring or rubber band or something rubber is called elastic energy. And so if you were to look it up in the textbook, for example, you would get this. Now, here's the thing. Because this is stored energy, it's often called potential energy. So the potential energy, or the elastic potential energy, or the energy stored in the spring, we use this symbol. It's a capital letter U to represent any kind of potential energy. So the potential energy of the spring is equal to 1/2 k x squared. So this is how we get the potential energy of the spring. It's 1/2 k x squared. That's going to be huge. Let's take this force concept. Let's take this force concept and go a little bit farther with it. Okay? What I'm interested in is a whole new. I'm interested in a whole new idea here. Is this was easy because you could store energy in something, right? But we don't necessarily have to store energy in something. Like a physical object, right? One of the things we know is that you could actually store energy in a field. So, for example, if I take this marker, if it's on the ground, if I raise it up to here, we know that there's energy stored somewhere. Okay? It's not in the marker because the marker's not different. It's not in the earth because the earth hasn't changed. Right? You can't store energy in the position of something because the position's not an actual thing. Like, where's the energy stored? Well, we say that the energy is stored in the gravitational field. So how do you store energy in a gravitational field? I'll give you a hint. You have to do work. Work is going to be the area here. So let's see if we can figure out how this happens. So here's the ground. Let's say there's a box on the ground. So there's a box on the ground, and you want to take this box, and you want to lift it up to here. Okay. You want to lift the box up to here. Well, how are you going to do it? Well, one way to do it, okay, one simple way to do it would be to, you just lift it up with your hands, right? Just lift it up with your hands. So our guy's going to lift it here. It was on the ground, and then when we look at it later, so here's our guy. He lifted the box up from here. The box has a mass m. How did he get it from here to here? He obviously had to lift it up. The question is, did he have to apply a force? Of course he did, right? But what happened here? Did we store some energy in the gravitational field? Yes, we did, because we know if we drop the box, it's going to fall back down. So how do we figure out how much energy is stored in the field? One way to do it is we know that the okay, we're going to have energy stored in the gravitational field. Well, let's see if we can figure out what to call that. Well, if it's stored energy, then it's going to be potential energy. So we're going to call it UG. This is what we're going to call gravitational potential energy. This is energy stored in the gravitational field. And that's going to be equal to the work, done while lifting it up. Well, how are we going to do that? Well, to do it, what we're going to do is we're going to apply our same understanding that work is the area of the XF graph. So let me draw it out.